Welcome. Thank you. Appreciate it.
All right. It is recording.
Yeah. Okay. Yeah. So hi everyone. My name is Mahmoud Abdul Karim. I will be introducing WebRTC for you today. The outlines for today are what is WebRTC, who uses WebRTC, supported browsers and platforms, WebRTC APIs overview, signaling protocols, NATS overview, WebRTC data channel, and multi-party architecture. And finally, I will show you a demo how two browsers can communicate between each other without the need for any external library. So what is WebRTC? WebRTC is a technology. It's a collection of standards and protocols that enable peer-to-peer real-time communication natively from a web browser. When we say natively from a web browser, this means that everything that you will be used, all the WebRTC APIs are implemented inside your browser. And WebRTC, actually, it's a media engine with JavaScript APIs. So finally, we will be using simple JavaScript APIs. So regarding the standards and development of WebRTC, the Web Real-Time Communication Working Group is the one that's responsible for defining the browser APIs. Also, the real-time communication in web browsers, it's the working group that's responsible for defining the protocols, data formats, and any other necessary information related to peer-to-peer communication in the browsers. I will show you a demo that's built on top of WebRTC. This application is something like Zoom, where you enter a room, and it's built on top of WebRTC. So as you can see here now that it starts streaming. I will show you today how you can do something like this with simple and easy steps. Yeah. So what are the supported browsers and platforms? Safari, Firefox, Chrome, Edge, and Opera, all of them are supporting WebRTC. iPhone, iPad, Android, Chrome, Mac, and Windows, all of them support WebRTC. Who uses WebRTC? Google Meet. Actually, this was the foundation of WebRTC. Then after that, Google decided to open the code for the Google Meet and then called it WebRTC. Messenger is using WebRTC, Discord, Amazon Chime, and many other applications around the world actually are using WebRTC. So what's different about WebRTC? The main thing here is that actually it's an open standard and free. After Google has released the WebRTC, it was a big milestone in developing real-time communication. It was something very difficult before the WebRTC actually. And I believe that there was no free libraries like WebRTC. And finally, it's web APIs. You are using simple web APIs, simple JavaScript APIs to use WebRTC. So the WebRTC contains three main APIs: the getUser media, the RTCPeer connection, and the RTC data channel. getUser media actually is responsible for gaining the access to your camera and microphone and device screen. The RTCPeer connection, it's responsible for encoding, decoding media, and send it over the network. Also, it takes care of net traversal and many other things. The data channel or RTC data channel, actually RTC has this API so that the peers can send any other thing rather than the video and audio between peers. So for example, if you want to, for example, like Zoom, we have the video call and we have chat. So the chat messages can be sent over that RTC data channel. I will show you a demo after the end of this session how we can do that. So getUser media. getUser media actually it's responsible for video and audio quality enhancement, steam synchronization, and network latency. As you can see here that we have the video engine and we have the voice engine. The video engine is responsible for video codecs, synchronization, image enhancement, and the same for voice engine. It contains the audio codecs, echo cancellation, and noise reduction. And these actually engines are wrapping your device hardware. So here actually we will have your camera, and here you will have your microphone. And these actually are wrapped by internal WebRTC API, which is built on C++. And then after that, we have the JavaScript wrapper that you will use on your browser. getUser media, actually, the media stream object is the primary interface here. It consists of one or more individual tracks. The input source, this input source for these streams could be your camera or your microphone, or could be a local or remote file. The output of this also can be sent to one or more destination, a local video or a remote peer, so the other peer. Also, the media stream is constrained by the capabilities of the input source. So it's, for example, the camera, the media stream will be constrained by camera features that you have. Let's see this code. So here we have the video HTML element, and then we have the constraints, as you can see here. The constraints actually are a set of options that apply to audio or video. So here we have the width, the height for the video, and frame rate, and more options actually. So the API that we'll use today for this is called, as we said, getUser media. getUser media takes 3 parameters. The first parameter is the constraints. The second parameter is the getStream, which is a success callback. Once the getUser media success, it will fire this callback and failure callback. And once the success callback is fired, all we need to do is to feed that stream from getUser media, which is get from your camera to this video HTML element. I will show you a quick demo after this slide. So we got the user media, we got the stream, then what? Then we need to manipulate the individual tracks, and then we can feed it into other browser APIs. Either we can feed it to web audio API, or the canvas API, or the video HTML element, or the WebGL APIs. You can feed it actually to the appropriate HTML element. And then actually we can send it over the network to the other peer after we got the stream. So I will show you a quick demo. Yeah, so as you can see here that this one actually uses getUser media, and here I can take a snapshot from this video. For this one, actually, as you can see here, that we are capturing now our camera and feed it to our DOM with a very simple and basic steps. I will show you the code for this and how simple is that code. So regard the HTML, we have the video, this one that we will feed the video from our camera to it. Sorry, I need to mute my phone. Okay, and we have the button that for taking a snapshot, and then we have the canvas, and that's it. Actually, it's very simple. For the JavaScript, we just querying the video, having the constraints. I make it simple, and then we have this API navigate media devices.getUser media. I give it the constraints and the handle the success callback and the failure callback. And on the success callback, as we said, we just feed the video from the stream to the video HTML element, which is this one. And for drawing the image, it's the same. Actually, we are using the canvas APIs. We just give it the video and the width and the height, and that's it. So this was the first API for WebRTC, which is called getUser media. Does anyone have any question for moving on?
Not so far.
Okay. The RTCPeer connection. The second API that we will talk about today is the RTCPeer connection. The RTCPeer connection actually manages the full life cycle of each peer-to-peer connection. It's relatively a simple interface. So we have covered this area, the voice engine and the video engine, and we will cover with the RTCPeer connection this area, which is on the transport layer. Yeah, so the RTCPeer connection actually is built on top of UDP. As you can see here, we have the RTCPeer connection and the data channel. It's preferred timelines over reliability. UDP actually is the foundation for real-time communication in the browser. The RTCPeer connection, as we said, that's used UDP. Or before actually moving to this slide, does anyone know what's the difference between TCP and UDP? TCP and UDP.
Yeah, because so TCP involves sort of acknowledging packets sent over and has more sort of error checking, whereas UDP is for is basically a little bit of a lower level protocol that we use in cases where you want to have more throughput and less of that sort of overhead from the TCP protocol.
Yes, you are right. Actually, you are correct. So for an application like that using WebRTC or video streaming, we will sure choose UDP for that, since actually we will prefer the time or the speed over the packet reliability and other things that you said, David. So RTCPeer connection is using UDP. In UDP, we have no guarantee of message delivery, no acknowledgements, no timeouts. With UDP, we have no guarantee of order of delivery. No connection state tracking, no congestion control. So actually, all of this is constrained by the UDP. So RTCPeer connection, we have these 3 steps. First of all, we need to know or to discover the peer that we want to talk with. After that, we will do something called signaling. And finally, after the signaling finish, the peer connection could be established. So let's see this picture. So basically, this is a user on Chrome that wants to talk with another one on Firefox. So before this connection is established, we need to share some information or to exchange some information between other. This process is called signaling. And after the signaling is finished, these 2 users can communicate with each other successfully. Signaling protocols. Signaling is not defined by WebRTC protocols. So WebRTC has nothing to do with signaling. It's up to you to choose the signaling protocol that you need. The signaling protocols that we have are, these are the famous ones, the socket.io, the SIP, and XMPP jingle, and the ICDN. Actually, maybe the most famous one is the socket. So again, WebRTC does not have nothing to do with you with signaling protocols. It's up to you to choose the appropriate one. So for signaling and session negotiation, actually, we need to exchange some metadata before the peer-to-peer connection is established. These metadata include session control messages. These messages actually are used to initialize or close the communication and report errors. It's used for, or the other thing that we can share with the metadata is the network. network interfaces information. So we mean here the IP addresses and port addresses for your network card. And then finally, the media capabilities. So what codecs that you have, what resolutions that can be handled by your browser and by the remote browser. So the signaling and session negotiation actually is exchanged in a standard data format called SDB. So it's using the STB protocol to send the data. The STB, as we said, describes session profile. Actually, it contains, as we said in the last slide, type of media to be exchanged, network interfaces, codecs, and others. So here are an examples. For example, this one, it's sending some audio information about your audio card. And for the second STB message, actually, we are sending the IP, your port, and other things over the network. And for example, this one actually is sending some codecs that you have, the browsers, your camera, or your audio device have. So actually, this was called STB message formatting. So one important thing to mention here is that once we need to exchange the STB for messages, the first thing that we will do is to that we will create an offer and then set the local description with this offer. And then we will send this offer over the signaling channel to the other peer. And once the peer is receiving that offer, it will set the remote description. Set the remote description means I'm setting the description for Amy. On Bob, I'm setting the remote description for Amy. And once Bob is set the remote description, then it will create an answer. And first it will set the local description and send it over the signaling channel. And Amy will receive that and it will set the remote description to that answer. So we need to understand this. Every peer needs to set the local description and the remote description at the same time. Let's see this code. The first step is the signaling channel. As we said, we have nothing to do with signaling channel. It's up to you to define it. Here we have the RTCPeer connection. The RTCPeer connection actually will create a new RTCPeer connection once created within you. And then after that, we know this API that we described before, navigator.getUser media. And once the success callback is fired, we will add that stream to the RTCPeer connection, this one. And then, as we said, we will create an offer. I will set my local description to that offer, and then I will send it back to the signaling channel to the other peer, so that the other peer can set that description. Before moving to NATS, does anyone have any question?
So whenever you're establishing, I'm sorry, can you hear me?
Yeah, I can hear you.
So whenever you're establishing the connection between the peers, is there like what sort of mechanisms are supported by like that standard for end-to-end encryption?
Yeah, you mean the security? And
sure. Is that coming up or is that?
Yeah, it's coming. Yeah.
Okay,
yeah.
Well, I'll wait then.
Yeah, okay. So what about NAT? The IP version 4 addresses actually are only 32-bit long. And NAT allow unregistered IP version 4 addresses or local IP version 4 addresses to access public internet using a single public IP address. And NAT actually can do this for us using something called translation table. Translation table contains mapping for your local traffic and your public traffic. So it will register your local IP address and local port address for each request. and to which IP address and to which port, public port address we have. So in the translation table on the router, we will have this translation table. And as you can see here on this picture, that actually all traffic from this network, all computers, all laptops are using this public IP address to access the internet, for example, this server. So, okay, so what's the issue with NAT? Why do we need to care actually about NAT? The issue here is that me as an internal client, and I want to connect to other peer, I am not aware of my public IP and public port address. So I need to know my public and IP address so that I can send that to the other peer over the signaling channel so that we can establish a connection. To be able to do this, we will use something called STAN server. STAN is a protocol. Actually, STAN allows us or allows a client application to obtain and get the public IP and port address for your device. So before starting the call, or you will talk to your STAN server. Hey, STAN server, please give me my public and port address so that I can talk to my peer. So this is actually the first thing that we will do. And what should we do when STAN is not working? 80% of the time, connection using STAN fails. Actually, STAN server will not work with all topologies. Some topologies have some network configurations that STAN will not work with them, like firewalls and other configurations. So at this stage, if the STAN server failed, then we will use another protocol called turn server. Turn is another protocol. It's only used as a fallback when the STAN does not work. And the sad thing here is that the connection, if the STAN server is not working, the connection is no longer peer-to-peer, since every information or everything for this call should pass using this relay server. So this is an important thing that we need to keep in mind, that if the STAN is not working, the connection is no longer peer-to-peer. Yeah, so the ICE protocol, the interactive connectivity establishment. The ICE is a protocol. Actually, the ICE protocol seeks to establish the most efficient tunnel between the participants. So the ICE protocol tries to find the most efficient path between two peers. It starts by try to have a direct connection where possible. It try to use STAN where needed, and if failed, it will use turn server. The IC, actually, each RTC peer connection, it contains an ICE agent. The ICE agent is responsible for ICE gathering process. The queries the ICE agent actually is querying the operating system for local IP address and port address. Okay, my phone keep ringing. Can I answer it? Excuse me, sorry.
Yeah, sure. Take your time.
Actually, I'm very sorry. My father is calling me. Okay. So we have talked about the ICEAgent. So the ICEAgent, actually, we said that it's responsible for as we said, I will just need to refresh your information. It's used for it's used to establish a direct connection where possible. It uses the stun, as we said, where needed, and then fall back to turn if it's failed. So the RTCPeer connection, actually, each RTCPeer connection defined has an ICEAgent. The ICEAgent will query the operating system for local IP address and port address. So the first step, it will ask the operating system, hey, my operating system, give me my local IP address and local port address. Then, if configured, it will talk to the stun server to retrieve the public IP and port address. And if configured, actually, it will establish the connection. And if the stun server fails, it will use the turn server. And whenever a new candidate is discovered on the network, the agent will automatically register it with the RTCPeer connection object, and it will notify the application via a callback called on ICECandidate. I will show you a demo with this. Yeah, okay. So here we have actually in this RTCPeer connection example, here we have the ICE configurations. It's URL for the stun server and the turn server. Actually, for the stun server, you don't need to define it since we have a default URL. And then actually we have seen this before: the signaling channel, the RTCPeer connection, the getUser media. The new thing that we have on this slide is on ICECandidate. So we said that whenever a new peer is discovered on the network, on ICECandidate will be fired. So here on this code, actually, we are checking if the ICE gathering state is complete, and if it is completed, then we will create the offer and send it over the signaling channel. Actually, I will describe that on details on the demo. Yeah, so we said this concept before, where we need to set the local description and the remote description for each peer. So it's a duplicate thing, I think. Yeah, okay. So the final API that we will talk about today is the RTC data channel. It enables bidirectional peer-to-peer exchange of data. It uses the RTCPeer connection session setup. Once the RTCPeer connection is established, the connected peers can open one or more data channel. It can be used with or without audio or video. It's reliable. It has reliable and unreliable delivery messages. You can have multiple channels with prioritization. Some use cases actually for RTC data channel are gaming, remote desktop application, real-time text chat, and file transfer. The RTC data channel uses HTTP protocol. The HTTP protocol actually supports multiplexing of multiple independent channels. It provides message-oriented API, flow and congestion control. HTTP actually supports multi-streaming and has secure data transfer. So as you can see here, that the data channel is using the HTTP protocol that actually is built on top of UDP. I will skip this also. I will talk about it on the demo. The WebRTC security, Alan. Actually, WebRTC specification requires that all transfer data must be encrypted. The WebRTC uses the DTLS, Datagram Transport Layer Security Protocol, for this purpose, for the encryption. It's similar to TLS protocol, but it's designed to work with datagrams. So Alan, actually, we are using the TLS protocol for the encryption here. Does that answer your question?
Yeah, I'm reading about it now.
Yeah. Final thing before the demo is the multi-party architecture. So when we have two peers only, the connection is very simple and each one can talk to the other very simply. But what should we do when we have more than one peer connection? We have many approaches. We have something called mesh network, where every peer is connected to the other on the network. We have the star network, where this guy is the Scrum, say the master for this network. And I think this one is mostly used is that we have the centralized distribution where we have a server that all traffic from the network will use this server. Yeah. So it's demo time. I will show you. Okay. I will show you how these browsers can use WebRTC to talk with each other. Okay. So I will copy this code and paste it on the console. And I will describe it now. So here we have the RTCPeer connection. We have talked about this, right? And the new thing here is the data channel. So each peer connection has an API called create data channel. We just need to give it a name. So to create a data channel, actually, between me and the other peer, I need to use this create data channel. And the data channel has callbacks like on message, on open, on close. These callbacks will be fired once I am receiving a message from the data channel, once the message is opened, once the channel is opened or closed. And then I will, as we said, we will use this RTCPeer connection to create an offer. And then I will set that offer to my local description. And then we will have this on ICE candidate. On ICE candidate, actually, as we said, it's discovered once a new peer is registered on the network, even including myself. So here, actually, I'm just printing the local description for myself. So here on ICE candidate, I still not connected to any other peer yet. So this message actually is related to my peer, or it's myself, let's say. So I will copy this. I will copy this and go to the peer and just replace this. Okay. This. And then I will copy this. I will describe that, just bear with me. Yeah. So as you can see here that we have the same thing here. We have a new RTCPeer connection. I'm just setting the offer to this peer. So I take this answer, this offer, I'm setting it to this as a remote description. Okay. Can anyone describe what I have did with this, copying this message and send it or paste it here? We have described this process. What's called Okay, this process is signaling. I'm doing it manually here because we're having a demo, but in real time you will have, as we said, a signaling channel to send these offers over the network. So I will get the answer. So this peer got this HTTP message, set it as a remote description, and for sure the local description has been set here. So for this remote peer, the remote description has been set, and this is the remote description, and this is the local description for this peer. So I will describe that again. Let's just bear with me. I will copy this answer and paste it here. This is the local. Yeah. Okay. I will copy this and put it here. Okay. I will minimize to let you see what will happen. Move this for, okay. Okay, what we can see that the channel is opened, as you can see here. A channel between these two peers is opened, and then I can use this API, this function to send a message, so I can see, hi, my peer. So as you can see that hi, my peer is printed here. I can reply to it, hello. And you can see that hello is printed here. So we are connecting two browsers with a real-time chat without the need for anything else. This is actually the power of WebRTC. I will describe the code again and I will finish this session. So here we have the local connection. We have the creating the new RTCPeer connection, and then after that we have the on-ice candidate. The on-ice candidate actually, as we said, will be fired once a new peer is registered on the network. So here, for example, at the first step, it will fire when I am registered. Then after that, I have created the data channel, and then I have registered the callbacks for the data channel on message, on open, and close. And then I have created the offer and set it as my local description. And for the second step, actually, I go to the peer, set that message, that local description as a peer, as a remote description here on the peer. So this one, this is an offer. I just pasted that from the local. And then, as you can see, we have the same thing, the RTCPeer connection on data channel and the callbacks that we have seen on message, on open, on close. And then actually we set the remote description with that offer that from my local peer. And then we have created an answer so that we can use it for our local peer. And this actually was a callback for sending the messages, sorry. It's a remote channel send message. And that's it. Do you have any question? No questions. Okay, I think that we can stop the recording. David?
Sure. Yep. Let me go ahead and stop it.